Welcome to the video DC Circuits 2 for the honor section. In this topical section, I'm going to break it up into three subparts. The first one, which is dealing with just series and parallel circuits, which is what we talked about and looked at in section alpha of the packet that we've been working on. In the reading, that's section 6, 7, 10, and 11. And what we're going to look at there instead of what we covered in class is how to find equivalent resistance. So here's a short little video about finding equivalent resistance in strictly series or strictly parallel circuits.
Let's consider the resistances in a couple of simple circuits. First, a series circuit with two resistors. These may be lamps or any electrical device. We label their resistances R sub 1 and R sub 2. It's often desirable to know what single resistor could replace the two resistors and result in the same current and same energy drawn from the battery or other voltage source. This is the equivalent circuit resistance. For a series circuit, R sub equivalent is simple enough. It's the sum of the individual resistors, because the same current has to pass through each of them in turn. Resistances add. If there were additional resistors in series, then the equivalent resistance would extend for n number of resistors in series. Now consider this parallel circuit. We know that current takes separate pathways in a parallel circuit. Current through one branch doesn't encounter the resistance of any other branch. The total circuit current is equal to the sum of the currents in each branch. That is, I sub total equals I sub 1 plus I sub 2. And from Ohm's law, substituting V over R for each of the currents I, the single equivalent resistor that can replace the two resistors can be calculated from this equation. And since the battery voltage is the same as voltage across each of the branches, we can divide the equation by V and get yum. So the reciprocal of the equivalent resistance equals the sum of the reciprocals of the two single resistors. More generally, the equivalent resistance of a parallel circuit with n number of resistors can be found from this extended equation.
Alright, so now in this next section, what if we have circuits that aren't strictly parallel or strictly series? Section 14 of the reading talks about what if you have ones that are both. And then in 17, 19, and 20, they go into Kirchhoff's loops and junctions, which we talked about in section beta of our large packet. In beta, we did the plotting of the voltages and the drawing of the currents, which led us to the linear equations. And I think reviewing those sections, those plottings and everything in beta would be very useful. The PowerPoints are up in our course documents. Instead, I think we could use this time to understand how to use a multimeter to measure voltage and to measure resistance in the circuit. So here's an instructional video about how to use a general multimeter.
I'd like to demonstrate now using a Fluke multimeter. This Fluke digital multimeter is a general purpose meter. It is fairly sophisticated. It does have some advantages over some of the other meters, but it is a fairly basic meter as far as digital multimeters go. Most meters will have the functions that we are looking at for measuring these basic functions for this DC supply. Okay, I'd like to first of all start with the measurement of resistance. Resistance is measured quite simply by using this meter, making sure that the red lead is connected to the volts and ohms of the meter, and the black lead is connected to the common lead of the meter. First of all, you select over to ohms, omega, here, and the meter will automatically turn on, and The resistance measurement, a loose resistor, is measured quite easily by putting the black lead on one side of the component and the red lead on the other side of the component to measure the resistance of, in this case, 0.988 megohms. The nominal value of this particular resistor is 1 megohm. It's very important to remember not to hold both sides of the component, the loose component, because it's very easy to measure the resistance across your body if you do that. For instance, if I held both sides by my hands here, it would change to 0.5 of a megohm, whereas the actual resistance reading is 0.9 of a megohm. It doesn't make much difference for smaller values of resistance. I've got a smaller value of resistor here, 3.83 kilo ohms, and if I hold both sides of this one, you read very much the same number. In fact, this is the same number. So the higher value of loose resistor, you would use the more effect of holding both sides of the component. I'd like to discuss looking at measurement of voltage. First of all, we have a power supply which we'll connect to the circuit, and moving the meter now to voltage, DC voltage. The black lead is connected to the negative or the black side of the meter or the circuit, and the red lead is connected to the other side, the red side of to measure the volts, 20.62. Any particular voltage can be measured within the circuit by strictly putting the leads anywhere in the circuit to measure a particular point in that circuit. Voltage may be read across a component, an individual voltage drop, by putting the black lead towards the black negative of the power supply and the red towards the red positive of the power supply, and a voltage can be read across a component. In this case, 5.12 volts.
All right, the last section is down here. It's 26 capacitors in series and 28 capacitors in parallel. And this talks about how do capacitors function in these two circuit arrangements. It's not something that we're going to talk about in class, but reading that you should do afterwards. And here is a video explaining how and the capacitors function in these arrangements and some concepts behind them.
Okay, in today's video, I am going to go over the rules for parallel and series capacitors. All right, now I'm not going to give an explanation about what the rules and the equations are. I'm just going to state them and kind of point out how they are opposite of each other. This is our parallel circuit. This is our series circuit, both capacitors. If we want to find the charge, the total charge on parallel capacitors, we can just add up the sum. They can add up the individual charges. So the way we usually state this is the sum of the charges on each of the individual capacitors, Q being the symbol for charge. The sum of the charge is equal to the total charge. Okay, that's the rule, as I like to call it, for parallel capacitors. Now for series capacitors, it's kind of the opposite. The total charge is equal to the charge on 1, which is equal to the charge on 2, which is equal to the charge on 3. So usually we calculate the total charge and then we make the assumption that they're all equal to the total. Okay, but it's also true, of course, you can just think of it as the charge on each of the capacitors is the same. And okay, those are the charge rules. The voltage, okay, the voltage of cross, or the potential difference across each of the capacitors, is equal to the voltage of the battery, because they're all connected in parallel. Excuse me, I almost said series. They're all connected in parallel to the battery, so they all get the full power from the battery, I'd like to say. Okay, now it's kind of the opposite for series capacitors. In order to get the total voltage, you can add up the voltage across, or the potential difference across each of the individual capacitors. In this case, the voltage is kind of spread out across each of the individual capacitors, and the sum of the voltage drops, excuse me, the sum of the potential differences across each of the capacitors is equal to the voltage of the battery. Okay? So those are the two rules for series and parallel capacitors, the charge rule and the voltage rule, and you can kind of see they're opposite of each other. Charge is atom, charges equal. Voltage is atom, voltage is equal. All right, now this is the equation. Now for parallel capacitors, it's nice to figure out the total capacitance, as I like to call it, or the equivalent capacitance, as it's really usually referred to. The total capacitance, the equivalent capacitance, just add up the capacitance of each of the individual capacitors. So usually given that, add them up, you get the total. Now for series capacitors, it's a little more complicated because you got to use that dreaded 1/over equation. So the total capacitance, or the equivalent capacitance, same thing, is equal to, well, the 1/over the total is equal to 1/over the capacitance of number 1 plus 1/over the capacitance of number 2 and plus 1/over the capacitance of number 3. And like I said, I made a video that showed you how to do that. Here I'm just kind of presenting the equations, and you can kind of see once again they're kind of opposite. And if you think of these equations in terms of the resistor equations, you'll know that you can kind of get the same feel for how they work out. Okay, so those are the equations for figuring out the total or the equivalent capacitance. And then I just want to point out that for each set of capacitors, whether they're in parallel or whether they're in series, you can use this equation that the charge is equal to the capacitance times the voltage. The charge is equal to the capacitance, and you can use that for parallel capacitors and series capacitors, just like you can use Ohm's law, V equals I times R, for resistors in parallel or resistors in series. Okay? So that's just a quick overview of the equations that we use for parallel and series capacitors. I think it's kind of good to see them all on one page. Compare the parallel ones to the series ones. Oh, that's so interesting. Cool.
All right, so a lot of material and a lot of things go over. Remember to, if you have any questions, there will be a section to ask the questions here, and then I'll see you in class.